Okay, can everybody see my screen? Okay, great. Okay. All right, so as I said, let's begin with a quick review of the topics we covered last time. Last time we began discussing sets. Okay. We talked about the elements or members of a set. Right. We talked about the empty set or the null set. All right. We talked about subsets and proper subsets. All right. We talked about when two sets are equal, so equality of sets. And that, I think, more or less covers the basic topics that we were discussing last class. Okay. Oh, we also discussed cardinality and power sets, right? So cardinality of a set and power set of a set. Okay. Remember, the cardinality of a set is basically its size. It's the number of distinct elements that it has, and the power set of a set is the set of all of its subsets. All right, so does anyone have any questions from the homework that they would like to go over? What is subsets within subsets? Well, it would just be an element of the set, I guess. If I understand your question, I'm not sure I completely understand it. Okay. All right, I see we have some people asking about question. Oh, I see. Okay, so let me. Okay, so let's start with that. Somebody's asking, what if you have a set that looks like this? Okay, so this is a set with a single element. This is the element in the set. So this, let's say I call this thing S. This thing is an element of the set S. Okay, so that's just a set that is an element of another set. Okay, so this set is an element of set S. Okay, so it's just an element of another set. Yeah, it's not 2. It's not the number 2. It's a set containing the number 2. All right. Okay. All right. So let's get to the homework problems. We're starting with number 9, apparently. Let me look this up 1 second. All right. From 9, we have a couple of requests. 9b. Any other parts from 9? 9b and 9d. All right. So let's look at 9b and 9d, and we can do any other parts there from that number if you want as well. So 9b. So the question is, determine whether each of these statements is true or false. 9b is this. The empty set is an element of this set. Okay. What do you guys say? Is this statement true or false? Is the empty set an element of that set that contains the number 0? True or false? Okay, we have one person, one brave soul has ventured an answer. He to say true. We have a couple of other brave souls saying it's false. Okay. It is, yeah, it is in fact false. Okay, it's not true. This statement is false. Okay. The empty set is not an element of this set. To be an element, right, we're not talking about subsets here, we're talking about elements. Okay. To be an element, the empty set would have to appear inside of the given set. Okay. The empty set does not appear anywhere inside of this set, so it's not an element of that set. Okay, it's false. To be an element of that set, it would have to look like this. This statement is true. Now the statement is true because I see the empty set here. It's an element. It's in there. Okay. All right. So that's 9b. Could I repeat that? Yeah, sure, again. So again, to be an element of a set, that item, that thing has to appear in the set. Okay, so if I look at this statement that was given, okay, the empty set, this thing, this object here, does not appear anywhere inside my set. I don't see it there. So it's not an element of that set. To be an element of the set, it would have to appear in there somewhere, but I don't see it. I'm looking at it. It's nowhere to be found. So this is a false statement. The empty set is not an element of the given set. Okay. The second one that I wrote is true because I see the empty set is an element of the set. I see it there with my own eyes. It's right there. It's in the set. Okay. So that second one would be true. Okay, so the empty set is a subset of all sets. Yes, so the empty set is a subset of all sets, but it's not necessarily an element of every set. Okay, so you got to distinguish between elements and subsets. All right, so let's look at part D. Is the empty set a subset, a proper subset of this set? Is that statement true or false? All right, we have a couple of different answers. Some people say true, some say false. This one is true. Okay, the empty set is a proper set of this set. Okay, all right, why? Well, remember, what is the empty set? The empty set is this. I'm just rewriting the same thing. Okay, the empty set is this. It's a set with nothing inside of it. That is a proper subset of this set, right? Because to be a subset, anything that appears in here has to also appear in here, okay? Nothing appears in here though, so it's automatically a subset of everything. It's even a proper subset of this set, okay? So it's true. This is question 9. Am I doing 11? No, I'm doing, in my textbook, this is number 9, all right? Some people might, if you have different editions, you might have different numbers, all right? Okay, all right. All right. Next, let's see. What problem should we do next? We had a request for 23. Let's look at 23. Actually, I see 21 first. So let's go to 21 first. And oh, no, before that, I see 11. Okay, let's do 11 first. All right. Okay, which part from 11? 11 C and 11F. All right, let's look at 11. Okay, again, same thing. Determine whether the statement is true or false. Part C is this statement. The set containing X is an element of the set containing X. Okay. What do you guys say, true or false? Is this a true statement or a false statement? Okay. All right. I see we have a mix of answers here. Somebody checked the answers in the back. It says false, but they don't know why. So yes, the answer is that this is a false statement. And let's explain why. Again, this is asking you, is this thing an element of the set? So how do we check if it's an element? I have to look at the thing exactly as it is and say, does this thing exactly as it appears here, does it appear inside the braces over here? Okay, and the answer is no. What do I have inside the braces on the right? I have an X. I don't have this inside, okay? So in other words, the statement would be true if it was written this way. That would be true. Now this thing is an element of the set because exactly as it appears on the left-hand side, it appears inside the braces on the right-hand side. Okay, this and this are not the same. But this and this are the same. So, okay, do you see that? Can it look like this? Somebody wrote something that looks like this. I think this is what you meant. Yeah, that's the same thing as this. Okay. Okay. All right, good. All right, so let's look at 11F now. Is the empty set an element of this set? So what do you guys say, true or false? Again, remember, what does element mean? Element, not subset. We have to distinguish. Element means that the item on the left appears exactly as it is inside the braces of the set on the right. So is this statement true or false? Right, this is false. Okay. False. Okay. Okay, remember, subset means that the elements inside the braces on the left also appear inside the braces on the right. Okay. Okay, so that was 11. And let's now move on to, I think the next question was 21. Let's see here. 21 A and C. Okay. Find the power set of each of these sets where A and B are distinct elements. Okay. 21, part A. So in part A, we're given the following set. And we're asked to find its power set. So let's call this thing S. So P of S is the set of all subsets of this thing. So what are the subsets of this thing? We know that the empty set is a subset of every set, and the set is also a subset of itself. So those two are in here. There's really nothing else. There's no other possibilities. Those are the only two subsets. So that would be the power set. Okay. Part C, you are given, I'm going to call it S, even though the problem didn't call it S. You're given a set S that contains two elements, the empty set and a set containing the empty set. Okay. All right. All right, so this is where it might get a little confusing here. So first of all, without looking at S, the empty set is a subset, okay? What's another subset? Another subset would be a set that contains the first element here. What's another subset? Another subset would be a set that contains the second element here. That would look like this. Okay. And finally, the last subset would be the set itself. So that would be this. Okay, so this would be the power set. Okay, let me erase these. Okay, so the subsets are the empty set, the set S itself, and then this set containing the first element from my set, and this set containing the second element from my set. Okay, and those would be the elements in the power set. Okay, so that was 21. Let's move on to the last question. I think, oh no, there were two more questions. I think 23 somebody asked about. Let me see here. Yeah, somebody asked about 23 A and C, and then was there another one? And then 41. Okay. How many elements does each of these sets have where A and B are distinct elements? Okay, you're given the following set. The power set of the set whose elements are A, B, and a set containing AB. Okay. So we're asked, how many elements does the power set have? So in other words, what is the cardinality of this set? Okay. So remember, if I have some set S whose cardinality is n, the cardinality of P of S, its power set, will be 2 to the power of n. Okay. In this particular problem, S is this set. So what's the cardinality of S? How many elements are in this set? How many distinct elements? What do you guys say? How many elements are in S in this problem? 3, exactly. Okay, so the cardinality of the P of S of its power set will be 2 to the power of 3, which is 8. So that's our answer, 8. Okay, let's do C. In this one, you're asked, what is the power set of the empty set? Oh, somebody asks, why 3? Why not 4? Okay, so let's answer that quickly before we move on to part C. Okay. Let's look at the set S here. How many distinct elements are there? There's the A, that's 1. There's B, that's 2. And there's a set containing AB, that's 3. 1, 2, 3. Okay. Yes, that is considered one element, the set containing the letters A and B. Okay. Okay. So let's look at this one now. So the cardinality of this thing, well, to know the cardinality of this thing, I first have to know what the cardinality of this is. In order to know what the cardinality of this is, I first have to know what the cardinality of the empty set is. What's the cardinality of the empty set? How many elements are in the empty set? Careful, 0, right? The cardinality of the empty set is 0. It has nothing inside of it, right? Remember, the empty set is this. It's the set that has no elements, so its cardinality is 0. There's nothing inside of it, okay? So the cardinality of the power set of the empty set will be 2 to the power of 0, which is 1. So that set has 1 element in it, okay? This set will be 2 to the power of 1, which is 2. So this set will have 2 distinct elements. So that's our answer, 2. Okay. All right. So that's this question. The last homework question was 41. You were asked to translate each of these quantifications into English and determine its truth value. So let's look at part A. You were given for all x in R, x squared does not equal to -1. Okay, so what is this statement saying? It's basically, now that we have symbols for the set of real numbers, the set of integers, instead of writing out the domain separately, I can include the domain in my quantification by using set theory notation here. So this is basically saying for all real numbers x, for every x in R, right, for all real numbers x squared is not equal to -1. Okay? In other words, there is no real number whose square is equal to -1. Right? So now, instead of writing the domain separately, with this new notation from set theory, we can include the domain in the expression, okay? So we can include the domain in quantified expressions by using set theory notation. Okay. 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 And again, if I wanted to, I could also rewrite this sentence the way I said before. I could write it as there is no real number whose square equals -1. I'm going to just leave it like that. Okay. All right, and then the rest are similar. Oh, is this statement true or false, by the way? It's true, right? Because x would have to be the square root of -1, which is imaginary. It's not real. Okay, so that's a true statement. Okay, that's true. Okay, and then the rest are similar. So I will stop there unless you had a particular one you wanted to go over. Can we do C? Yes, sure, we can do C. C was the statement for all x in Z, so for all integers, x squared is greater than 0. Okay, this is saying for all integers x squared is greater than 0. In other words, every integer squared will be positive. All right, so that's the square of every integer is positive. True or false? Be careful. Remember 0. 0 squared is 0. It's not greater than 0. So this statement is false. Okay? All right, so the counter example is x equals 0. 0 squared is not greater than 0. Okay. All right, any other questions? Last call. Okay. All right, so we're now, I'm going to go back to some new material. We're going to finish up section 2.1 first, and then we're going to move on to 2.2. Okay. All right, so we are in 2.1. We're now going to discuss truth sets and quantifiers. Okay, so first let's define what a truth set is. All right. So given a propositional function p of x with some domain, the truth set of P, right, is the set of elements in the domain for which P of x is true. Okay, so a truth set of a propositional function is basically just the set of elements from the given domain that make the statement true. Okay, so it's just the set of numbers for which this statement is true, or a set of elements for which the statement is true. Okay. All right, so let's see an example. Example, let's say A. What is the truth set of the following propositional function, P of x, where P of x is the statement the absolute value of x equals 1, where the domain is the set of integers, where the domain is z. Okay. What is the truth set of this statement where the domain is z? Okay. So in other words, what elements from the domain make this statement true, right? So we have a suggestion here in the comments. Somebody has suggested that the truth set is the set containing the numbers -1 and 1. You are correct. Okay. All right, so the truth set here, let's call it T. All right, the truth set T is the set containing the numbers -1 and 1, because those are the two numbers for which this statement is true, right? The absolute value of -1 is 1. The absolute value of 1 is also 1, right? So those are the two elements in the truth set. Okay, so that would be our answer. All right, let's try another one. Let's say P of X is the statement the absolute value of X is equal to X. What is the truth statement of this same domain? Domain is Z. What's the truth set of this thing? Okay. So for which integers is this statement true? For which integers is the absolute value of X equal to X? Somebody suggests all integers. And somebody suggests those greater than or equal to 0. And the third suggestion, all positive. Another suggestion, all negative and positives. I'm not sure what that one means, but okay, we have a few suggestions here. Let's see. Okay. For every positive integer, right, the absolute value of 1 equals 1, the absolute value of 2 equals 2, right? So for all positive integers, it's going to be true. Okay. Is it true for negative integers? Is the absolute value of -1 equal to -1? No, right? Is the absolute value of -2 equal to -2? No. So it's not true for negative integers. It is true for positive integers. What about 0? Let's check 0. Is the absolute value of 0 equal to 0? Yes. So it's true for every integer greater than or equal to 0. What do we call that set? The set of all integers greater than or equal to 0. Does anyone remember what that set is called? 0, 1, 2, 3, 4. Last time we gave it a name and a special symbol. Yeah, n. It's the set of natural numbers. Okay, so the truth set is n. It's the set of natural numbers, right? 0, 1, 2, 3, etc., etc. Okay, let's do one more. Let's say P of X is the statement x squared equals 3. Okay. What's the truth set for this? Again, domain is Z, let's say. Set of integers. What's the truth set of this thing? Somebody has suggested the empty set. Another suggestion, the square root of, or positive and negative, the square root of 3. Well, let's see. For this to be true, what would X have to be? If I take the square root of both sides, I get X would have to either be positive or negative the square root of 3. Is positive or negative the square root of 3, is that an integer? No, it's not. So therefore, it's not in the domain. Okay, so our answers have to come from the domain. This number here, these two numbers are outside the domain, so we're not looking at them. We can't include them. So our answer here would be the empty set. Okay. All right. Okay. Excellent. All right. Very good. Okay, so those are truth sets. Let's now discuss Cartesian product. Okay, so any questions on truth sets? Okay. All right. So we're now going to discuss something called Cartesian product. First, we're going to define something called an ordered n-tuple. Okay, so remember in sets, the order does not matter. There is no order in a set. In an ordered n-tuple, the order of the elements does matter. So there is a first, a second, a third element. Okay, so let me give you a definition of what an ordered n-tuple is. All right. So the ordered n-tuple, all right, usually written this way: a1, comma, a2, comma, a3, comma, dot, 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 comma, a sub n. Okay, so it's called an n-tuple because it will have n elements in it. All right, so the ordered n-tuple, written this way, is the ordered collection. Okay, so there's order here as opposed to a set that has a1 as its first element, a2 as its second, so on and so forth, and an as its nth element. Okay, so that's what an ordered n-tuple is. Okay, so for example, okay, this is an example of an ordered three-tuple. Why a three-tuple? Because it's got three elements. Okay, it has a first element, a second, and a third. The first element here is 3, the second element is 7, and the third is 5. Okay, so it has order. So this, because order matters, this three-tuple is not the same as this. Okay, if I change the order, it's a different n-tuple. So this is a different three-tuple. Okay, order matters. Okay. Another example, I can give you an example of a two-tuple. Let's say 10, comma 8. This is an example of a two-tuple. All right. What's another name for a two-tuple, by the way? Does anyone know what another name for a two-tuple is? Not just a pair. That's half the name. You're missing the first word. An ordered pair, yeah. A two-tuple is another name for a two-tuple is an ordered pair. Okay, all right, which you're probably familiar from that term from graphs, right? And every point on a graph is an ordered pair, right? It's a two-tuple, right? Also called an ordered pair, because it's a pair of numbers. A pair is 2, and they have order. Right? There's a first and a second. Okay. A set. So somebody's asking, why is it called ordered? Okay. So what do we mean by order? Okay, so we have two questions here. An n-tuple is ordered as opposed to a set. In a set, the order doesn't matter. Now, what do I mean by order? There was a second question here. By order, I mean that there is a first, a second, and a third. So here, this is ordered because 10 is considered the first element, 8 is considered the second. Okay, in a set, right, let's say I had a set, here order doesn't matter. So this is the same thing as this. I don't care about first, I don't care about second. In n-tuples, the order matters, meaning that there is a first element, a second element, and a third element. So this is not the same as this. Okay, if I change the order of the numbers, then I've changed the n-tuple into a different n-tuple. Okay, it means something different. Okay. Yes, that's correct. Okay, no problem. Okay. Oh. Yeah, that's correct. Only a two-tuple is called an ordered pair. Okay, it's a special name for a two-tuple. Okay, all right. So now we can create n-tuples from sets through a process known as a Cartesian product. Okay, so let me give you the definition for what a Cartesian product is. Okay. All right. Let A and B be sets. The Cartesian product, named after René Descartes, for those of you familiar with René Descartes, let A and B be sets. The Cartesian product of A and B, denoted by A times B, is the set of all ordered pairs A comma B, where the element lowercase a is an element of the set A, and B is an element of the set B. Okay, so hence we have the following. Okay, A times B, the Cartesian product of the sets A and B, equals to the set of all ordered pairs A comma B, such that A is an element of A and B is an element of B. So I just wrote it here using set roster notation. Okay. All right. Just give me one moment. Okay. Let's see. We have some questions here. First bracket is used for tuple. What is the line after A comma B? All right. Let's see. Let me look at this thing here. Okay. All right. So let me again explain what we're saying here. So if you take two sets A and B and perform their Cartesian product, what we're doing is we're creating a new set. Okay. So a Cartesian product of two sets creates a new set. All right. It takes the elements from A and the elements from B, and it turns them into two tuples. All right. So this new set, the Cartesian product, its elements are all two tuples, are all ordered pairs. Okay. So let me show you an example. All right. So this says where the last line here is where A is an element of A and B is an element of B. Okay. So let me show you an example of what we mean here. Okay. Okay. Let's say I have a set A whose elements are, let's see, 1 and 2. Okay. And I have a set B whose elements are the letters X, Y, and Z. All right. The Cartesian product of A and B is a new set whose elements are all the ordered pairs that I can make from these two sets where the first element of every ordered pair will come from A, and the second element of every ordered pair will come from B. So what's one ordered pair I can make from this thing? Well, I can make an ordered pair where the first element is 1, which comes from A, and x, which comes from B. So that's one element in this Cartesian product. Okay, notice the first element comes from A, the second element comes from B. If I move on to another ordered pair, what's another ordered pair I can create? Another one would be to have the ordered pair whose first element is 1 and whose second element is y. A third would be an ordered pair, 1 comma z. Okay, another ordered pair I can create is 2 comma x, another is 2 comma y, and then 2 comma z. That's the last one I can create. Okay, so this is the Cartesian product of A and B. It's this new set whose elements are all ordered pairs. Okay, where the first element of each ordered pair comes from the first set, A, and the second element of every ordered pair here comes from the second set, B. Okay, so x comma 1 is not an element in this set because x comes from B and 1 comes from A. Okay, so this is in the wrong order. So this one is not an element in this set. Okay. Can we make a cubic product in the same way? Yes. So if you wanted to make a set of 3 tuples, you could have A times B times C, and that would be the set of all 3 tuples, right? A, B, C, such that A is an element in A, B is an element in B, C is an element in C. Okay, and so on and so forth. Right? I could also have A squared, right? A squared would just be A times A. Right? That would be the set of all, well, all ordered pairs, such that A1 and A2 are elements of A. Okay, and so on and so forth. So I could play with this in a bunch of different ways. Okay. Can it be 1y, then 1x, then 2z? Yes, it can. Okay. So here, within the order, each ordered pair, I can't change the order, but within the set, the order doesn't matter. So I could rewrite this. This is the same thing as writing 1 comma y, then 1 comma z, then 2 comma x. Okay, so within the set, the order doesn't matter. Okay, just the ordered pairs themselves have to be 1y, 1z, 2x, but I can rearrange them however I like within the set. Okay, because within the set, the order doesn't matter. Yes, x1 would be in the set if it was b times a. That is correct. Okay. Okay. All right. Any other questions on Cartesian products? Okay. All right. So Cartesian products are really helpful when defining relations, which is not really something we're going to get into in this class. But let me just give you this definition briefly anyways, in case you ever see it later on. So a quick definition. A subset, we'll call it R, a subset R of the Cartesian product, A times B, is called a relation from the set A to the set B. Right, and then later on when we define functions, a function is also sort of like a relation. But like I said, we're not going to really deal with relations in this class, so I'm not too worried about that definition. Okay. All right. Final questions on Cartesian products. Okay. All right, we're now going to move on to section 2.2, which deals with set operations. Okay, so we're going to discuss a couple of different set operations in this section. You probably have seen or have heard of many of these operations previously. We're going to talk about the union of two or more sets, the intersection of two or more sets, the difference of two sets, and so on and so forth. Okay. So let's start with the definition for the union of two sets. And so let A and B be sets. The union of A and B denoted by that, right? So that's the union of A and B. Okay, it's a U-like symbol. Is the set that contains those elements that are either in A or in B or in both. Okay. All right. If I were to write this definition out using set builder notation, I said set roster earlier, I think. Set builder notation. Set builder? Yeah. I would write it out as follows. So the union of A and B is the set of all elements X such that X is an element of A or X is an element of B. So it sort of corresponds a little bit to disjunction, right? It's in A or in B or in both. That's a disjunction. So notice the U and the V for disjunction are both opening upwards, the same direction. Okay, so for example, let's say I have a set A, and A contains the elements 1, 2, 3, and 4. And I have a set B. B contains the elements 3, 4, and 5. The union of A and B is a new set that contains all the elements that are in both sets. So it contains the elements 1, 2, 3, 4, and 5. I'm not going to write repeats. Okay. So that would be the union of these two sets. Okay. I can also represent a union of two sets using a Venn diagram, right? I'm sure most of you are familiar with Venn diagrams. So with Venn diagrams, we represent sets usually with a shape. So usually a circle or a box. I will represent my sets with circles. Okay, so let's say I have a circle, and everything inside this circle represents the set A. And let's say I have a circle here. This circle represents the set B. Okay, so the union of the two sets would be represented by the shaded area, which I'm shading in now. It's everything. Okay, so this is A union B is the shaded region. Okay, so if I draw a Venn diagram for my above example, okay, here's the set A, here's the set B, all right. 1 and 2 are numbers in A, 5 is a number in B, and then 3 and 4 are the numbers that A and B have in common. So those numbers go in the middle here, right? This middle region represents those numbers that A and B share, or those elements that A and B share. Okay. All right, so that's how the union of two sets works. All right, let's now discuss the intersection of two sets. Okay, so the intersection of A and B denoted by this symbol here, so the upside down U, that's the intersection of A and B, is the set containing those elements in both A and B. Right? In other words, it's the set of elements that A and B have in common, the elements that they share. Okay, so if I were to write this out using set notation, the intersection of A and B is equal to the set of all x such that x is in A and x is in B. Okay, so that's an and, that's a conjunction. All right, so it's equivalent to a conjunction. All right, so for example, let's go back to my sets A and B from above. A contains 1, 2, 3, 4. B contains 3, 4, 5. The intersection of A and B is a new set, and the elements in this set are the elements that A and B share. So which elements are both in A and in B? The numbers 3 and 4. And again, we can demonstrate this by using a Venn diagram. Okay, so if this circle represents the set A, this circle represents the set B, then their intersection is the overlap, right? It's that shaded region there. So the intersection of A and B is the shaded region. Okay. All right. What happens if A and B do not have any elements in common? Okay. What would their intersection be? Okay, so let's say A and B, they don't have any elements in common. So their intersection would be what set? Yep, the empty set. Exactly. Okay. Right, it's the empty set. So whenever that happens, whenever the intersection of two sets is empty, they're called disjoint. Okay, so let me give you that definition, and then I will take any questions. All right, so two sets are called disjoint if their intersection is the empty set. Okay. All right, so let me take some questions if anyone has any questions at this time. Let's see. Somebody asked if it's all elements of A and B, then why use a V instead of a upside down V? I'm not sure what you're referring to. If you wanted to clarify your question, if not, that's fine. And then somebody asked, can we go up for a second, please? What would you like me to go up to if you still want me to go up? Ah, okay, excellent. Okay. Okay, no problem. Okay, so is there anything that anyone, I went a little fast through those two definitions, the three definitions here. Does anyone want me to go back to anything or review anything quickly before I continue? To the definition of intersection, yes, sure, let's do that. No problem. Okay. All right. Okay, anything else anyone wants me to scroll back to, or we're good? Okay. All right. Let me also now give you something called the principle of inclusion-exclusion. I'll give you that quickly. It's something we might see again later. The cardinality of the union of two sets Okay, so set A has some cardinality. Remember, cardinality is the size, it's the number of distinct elements. Okay. So A has a cardinality, B has a cardinality. The cardinality of their union is equal to the cardinality of A plus the cardinality of B. Okay, but if I do that, I'm adding their intersection twice. So I'm going to have to subtract off the intersection of A and B once. Okay, all right, if let's say this is A and this is B. Okay, if I add the number of elements in A together with the number of elements in B, then whatever is in their intersection, I'm adding twice. So I'm going to have to subtract off the intersection once so that I don't count those elements twice. Okay, so this is called the principle of inclusion-exclusion. All right. So for example, let's go back to the example we had above. Okay. The cardinality of A is 4. The cardinality of B is 3, right? A has 4 elements, B has 3 distinct elements. The union of A and B is 1, 2, 3, 4, 5, 6. Okay. Its cardinality is 6, right? Now, if I just added the cardinality of A and the cardinality of B, I would get 4 plus 3, which is 7. Okay, why? Because I've counted 3 and 4 twice. 1 second. Excuse me. I counted just 4 twice. Okay. I counted 4 twice. This is a different example than the one I gave above. I apologize. All right, 4 here is counted twice. All right. 4 is also in the intersection of A and B, right? The intersection of A and B includes 4. And the cardinality of the intersection of A and B is 1. So I'd have to subtract off minus the intersection, which is 1, which gives me 6. Okay, so the cardinality of A union B equals to the cardinality of A plus B minus the cardinality of the intersection. Okay. Let's see. Oh, can I draw the diagram that I erased? Yeah. Basically, I drew this. Okay. I was saying that if I just add the cardinality of A to the cardinality of B, I count the intersection twice. Right? That's counted twice. So I have to subtract it off once. Okay. All right. All right, moving on. Let's define now the difference of two sets. Okay, so definition. The difference of A and B, denoted by A minus B, is the set containing those elements that are in A but not in B. Okay, so A minus B is the set of all elements that are in A but not in B. So it's whatever A does not have in common with B. Okay. The difference of A and B is also called the complement of B with respect to A. Okay, so let's say these are our sets A and B. A has the numbers 1, 2, 3, 4. B has the numbers 3, 4, 5. A minus B would be the set of everything that's in A, but that's not in B. So we remove from A, we subtract from A all those elements that are in B. So A minus B would be the set of elements 1, comma 2. Okay, we remove basically the intersection. Somebody asked, no 5. Right, there is no 5 because we're not, what we're doing is we're taking the set A minus B means look at the set A and remove from it everything that it has in common with B. Okay, so we're not adding anything to A, we're just taking A, we start with A, and we remove from it those elements it shares with B. Okay, so I start with this, and I take out whatever B has that it has. So B has a 3, so I remove a 3. B has a 4, I remove a 4. Okay, I'm left with only 1 and 2. What would B minus AB, by the way? That would be the opposite, right? That would be take the L set B and remove from B everything it shares with A. So from B, I would remove the 3 and the 4. I'd be left with a 5. Okay, so B minus A would be that. Okay. Okay. All right. Let's now discuss the universal set. Okay. So for the next definition, I'm going to refer to something called a universal set. A universal set is basically just like a domain. Think of it like a domain. It's the set of all elements that I'm dealing with. So universal set is basically the same idea as a domain. Okay. All right, so if I have some universal set, if I draw it out with a Venn diagram, I'm going to call my universal set U. All of the sets that I'm dealing with will be inside U. So my set A, my set B, let's say I have some set C, et cetera, et cetera. Okay, everything exists inside this big universal set. Okay. So for example, a universal set could be like the set of real numbers, and then all of my sets that I'm dealing with will come from the real numbers. Okay. All right, so for my next definition, let U be the universal set. The complement of the set A denoted by A bar, A with a bar over it, is the complement of A with respect to U. In other words, A bar is equal to U minus A. It's everything in the universal set that's not in A. Right? So if I were to draw a Venn diagram, okay, if this is my universal set U, this is the set A. A bar is everything outside of A. So it's the shaded region here. So A bar is the shaded region. Can we use a prime instead of a bar? For our purposes, our textbook uses the bar notation, so that's what I'm going to use. All right. If you want to use a different notation, then just make sure you clarify for me what you mean. Okay. Okay. So for example, let's say my universal set is the set of integers. Okay. And A is equal to the set, well, let's write it this way. It's all x such that x is an integer greater than 10. Okay. What would a bar be? A b bar would be the set of all integers x such that x is less than or equal to 10. It's everything else. Okay. So a bar is everything else. Everything that's not in A, that's in my universal set. All right. Any questions on that? Okay. All right. If there's no other questions, we will stop here for today. Oh, would you like me to go over something? All right. Oh, let me also mention, I plan to have our next quiz next week. Let's do it next week for Wednesday. Okay. Next week, Wednesday. All right. So I will remind you again on Monday. Somebody's asking, this last part was confusing. All right. So let me just quickly go over that. All right. In the meantime, everyone, you can do the attendance. Will Monday's lecture be in the quiz? We will discuss on Monday. Okay, we'll discuss it. We'll see what we get to on Monday. All right. The last part somebody said was confusing. So I assume you mean my example here. So again, if A is, let's say, everything greater than 10, so 11, 12, 13, etc., etc., a bar is everything in my universal set that's not in A. So if my universal set is the set of integers, and A is the numbers 11, 12, 13, etc., A bar is everything else. It's everything that's not in A. So that would be 10, 9, 8, 7, etc., etc. Okay. Okay. I hope that clarified that. Okay. Let's finish up attendance here. Yeah, somebody has a question?
Yeah, I just want to see some notes. Could you go up to the tuple part? I could take a...
Oh, you want to go all the way back there? Sure.
Yeah.
Sure. Okay. Let me... Here?
Yes.
Okay.
Okay, that's all I need.
No problem. Anything else?
Oh, and a little bit under the disjoint part, if you could.
Sure. Also, somebody wanted A times B times C. Let me go to that. That's here. Okay, that's A times B times C. And then for disjoint. Here. Two sets are called disjoint.
Yeah, right under that.
Under it? Yeah.
Yeah, right under the example for disjoint.
Okay. Oh, the for example for disjoint is above it. All right. This is.
Oh no, the part. I guess not the example for disjoint. The part under it.
This is not disjoint. This is the principle of inclusion exclusion. That was
okay. Oh, okay. They counted twice. Okay, got it. Thank you.
Okay, no problem. All right, let me stop recording here.